It's November 8th, 2025. The solar data has finally stabilised. For days, astronomers across the world have been reviewing one strange pattern, something that happened just as 3i Atlas passed closest to the Sun. At 1.36 astronomical units, it should have behaved like a typical comet under intense radiation. Instead, instruments recorded an abrupt, localised change. Not a breakup, not a flare, but a momentary shift in motion and brightness that doesn't fit any known thermal model. This wasn't subtle. For nearly 3 weeks, 3i Atlas had maintained an almost mathematically perfect trajectory, unmoved by the small, uneven jets of vapour expected from its surface. Then, in the hours surrounding perihelion on October 29th, that precision vanished. Observatories from Chile to Hawaii caught it, a measurable directional change followed by a sharp spike in luminosity, and then silence. For the first time since Oumuamua, data from multiple agencies don't align. NASA's JPL reports a slight acceleration away from the Sun. ESA's solar orbiter notes a temporary reduction in dust output, and an independent team using the Very Large Telescope recorded something else entirely, a spectral shift inconsistent with reflected sunlight. It's as if 3i Atlas responded to the Sun rather than merely endured it. But the question now isn't what the Sun did to it, it's what it did near the Sun that no one expected. And that's where the story begins. On October 29th, 2025, 3i Atlas reached its perihelion, the point of its closest approach to the Sun. At that moment, the object was exposed to more than 700 watts of solar radiation per square metre, enough to strip volatile material from any comet-like body. Astronomers anticipated a flare-up, perhaps even a temporary breakup event. Instead, what they observed was precision. The interstellar object held its course with eerie steadiness for days leading into perihelion. The Solar and Heliospheric Observatory, SOHO, tracked it continuously as it skimmed the outer boundary of the Sun's active zone. No deviation, no unpredictable jets, not even the faint perturbations caused by asymmetric heating, the kind every comet exhibits when exposed to solar flux. Then, without warning, the readings changed. A spike in brightness appeared in multiple datasets within a window of just 4 minutes. The signal wasn't gradual like sublimation, it was instantaneous. For a brief period, 3i Atlas appeared almost reflective, its albedo increasing to levels that made no sense for its composition. Some researchers thought it could be a software glitch, but 3 separate observatories confirmed it. The object's visual magnitude brightened sharply, then stabilized again as though nothing had happened. At nearly the same moment, a new non-gravitational acceleration was detected. The Pan-STARRS system in Hawaii recorded a slight deviation, subtle but consistent. The object's trajectory curved away from the predicted path by a fraction too large to dismiss as noise. It wasn't random either. The deviation was directed almost perfectly away from the solar vector, suggesting a controlled or at least coherent impulse. For those watching the telemetry live, it was a moment of disbelief. Cometary outgassing can cause such accelerations, yes. But the timing was off. Outgassing peaks hours before or after maximum heating, not at the exact moment of maximum solar exposure. Moreover, the direction of the impulse didn't match the known structure of its tail. If jets were responsible, they would have forced the object to rotate erratically. No such rotation was seen. In the following hours, the Parker Solar Probe, coincidentally aligned for a partial observation, detected a localized density fluctuation in the solar wind. A compression front passed through the region just as 3i Atlas crossed it. The probe's instruments recorded an electromagnetic disturbance that some analysts now associate with the object's proximity. It was faint, short-lived, and spatially limited, yet perfectly coincident with the anomaly. It is rare for solar events and interstellar trajectories to align so precisely. The probability of coincidence is low, but not impossible. Still, the scientific unease comes from the sequence, not the coincidence. The brightness surge happened first, the electromagnetic irregularity followed. Then came the acceleration, a neat chronological order, one that implies causation, even if we don't understand the mechanism. Astronomers who study dynamic modelling began reprocessing orbital data immediately. The official line from the Minor Planet Center remains cautious. The deviation is within the range of possible non-gravitational perturbations. Yet behind closed doors, the analysts admit something different. No known comet from the Oort cloud or beyond behaves with such delayed precision. 3i Atlas seems to respond rather than react. At Mount Lemmon Observatory, a team comparing brightness evolution noted that the flare-up did not match any known spectral behaviour associated with dust or gas. There was no rise in carbon or oxygen emissions, no water signature at all. The object brightened as if reflecting sunlight, not emitting it, more like a mirror than a comet. And while that was happening, the sun itself was restless. AR 3510, one of the largest active regions of this solar cycle, erupted twice during 3i Atlas's perihelion window. Both eruptions were directed toward the object's quadrant. One of them released a coronal mass ejection, strong enough to disrupt magnetometers on Earth 2 days later. Yet despite passing through an environment dense with charged particles, 3i Atlas remained structurally intact and strangely stable. The data from ESA's solar orbiter adds another layer. Its heliospheric imager caught a faint arc of light moving with 3i Atlas. Not a tail, but an asymmetric halo. When the team enhanced the images, they found a localized region of brightness offset from the nucleus by several hundred kilometers. Some hypothesized this could be a detached fragment or dust plume. Others that it's something reflecting sunlight independently, like a secondary object. But this leads to another mystery. The halo dissipated almost instantly once the object moved beyond perihelion. If it was a dust emission, it should have expanded and persisted for hours or days. Instead, it faded within minutes, as if whatever reflected that light had simply stopped doing so. For scientists who have tracked hundreds of comets, that kind of behaviour is virtually impossible. Nothing about 3i Atlas fits the expected thermophysical model. The light curve resembles an artificial flash, instantaneous, concentrated and self-limiting. But before drawing conclusions, researchers are forced to return to fundamentals. The sun's energy output in that window was extraordinary. Solar flux variations were recorded at nearly double average levels for this phase of the cycle. The interstellar object may have encountered an electromagnetic surge beyond anything modelled in standard heliophysics. If that surge interacted with a conductive surface, metallic, carbon-rich or otherwise atypical, it could theoretically produce transient reflection or emission. Yet this explanation creates new questions. Conductive surfaces aren't typical of natural comets. Neither is the absence of volatiles, or the sustained structural integrity under such radiation. It's as though 3i Atlas is built differently, or at least composed of materials unfamiliar to our catalogues. That single event near the Sun has now forced scientists to reassess months of data. From its photometric evolution to its rotation curve, the anomaly isn't just about what happened, it's about what didn't. No disintegration, no jetting, no thermal lag, only a single deliberate-looking change. And in that stillness a pattern emerges, one that will dominate every subsequent analysis of its behaviour. Because when 3i Atlas passed closest to the Sun, it didn't break apart. It acted as though it adjusted. And that's when scientists realised something about this object isn't following the rules of comets at all. When 3i Atlas was first identified as interstellar, its trajectory appeared to obey every conventional expectation. Its orbit was hyperbolic, a clear signature of an object not bound to our Sun. Its approach, velocity, inclination, and light curve resembled a faint, inactive comet. Nothing at first hinted at the kind of defiance to physics it would later display. By late October, the global scientific community had a clear set of predictions for what should occur during its solar passage. The models were consistent. Intense heating from the Sun would trigger sublimation of volatiles, generating visible jets that would in turn produce a measurable non-gravitational acceleration. Its brightness curve would rise gradually as surface ice vaporized, and its spectral signature would shift toward the blue as dust scattered sunlight. That's what comets do. That's what Oumuamua didn't, and that's why scientists were watching 3i Atlas so carefully, to see whether this third interstellar visitor behaved more like a comet or like a mystery. But as the data poured in, something subtle became clear. The predicted thermal activation never occurred. 3i Atlas showed weak, inconsistent outgassing in the weeks before perihelion, but no large-scale sublimation. The comet's coma remained faint, almost sterile, as if sealed. Even under direct solar radiation, its thermal curve barely changed. The discrepancy began small, a minor difference between thermal emission and photometric brightness. But as the object neared the Sun, the mismatch widened into an outright contradiction. Instead of brightening gradually, it stayed dim, then flared once, abruptly, and stabilized again. It was as though it had skipped every intermediate stage. Researchers at the University of Arizona's Lunar and Planetary Laboratory modelled these behaviours against all known cometary databases. The output graphs were empty of parallels. There was no analogue in any of the thousands of comets previously observed. The lack of water vapour in the spectral data was particularly telling. A comet this close to the Sun should be venting H2O, CO2, and CO in distinct ratios. None appeared. If not gas, then what was producing the light? The most basic explanation was reflection, sunlight bouncing off a smooth or metallic surface. But for that to be true, the object's reflectivity would have to rise tenfold within minutes, and then return to normal. That would require a sudden, coherent change in surface structure, like a plate rotating, a shield unfolding, or a layer shedding in a single synchronized event. The models can't describe such a transformation without invoking deliberate geometry. Still, astronomers remain disciplined. Coincidence, not control. Physics, not intention. Every explanation must exhaust natural mechanisms first, so they turn to fragmentation. Maybe a surface layer fractured, exposing fresh ice that reflected more light. But again, the timing fails to align. The object's rotation period is too slow for such a precise event to coincide exactly with perihelion, and if ice exposure were responsible, spectrometers would have detected volatiles afterward. They didn't. Then came the outgassing hypothesis, the standard explanation for anomalous accelerations. Outgassing occurs when sublimating gases escape from one hemisphere faster than the other, pushing the object like a weak thruster. But to create the acceleration observed in 3I Atlas, the gas output would need to be enormous. That kind of force leaves an unmistakable signature: rotational torque, wobble, and coma asymmetry. None of those appeared in the light curve. To many researchers, this is the moment the data stopped behaving like science and started behaving like a signal, because what 3I Atlas did wasn't just wrong, it was consistent in the wrong way. The deviations were too clean, too symmetrical. At the European Southern Observatory, analysts tried reconstructing the object's brightness pattern using a reflective body model rather than a dust scattering one. The results were closer. The object behaved more like a solid reflector than a diffuse emitter. Its light faded with angle as if specular, not isotropic. In simpler terms, it looked shiny. That word, shiny, doesn't exist in the vocabulary of comet physics, yet it kept appearing in observational logs from independent telescopes. Specular reflection, one report reads, angular phase response inconsistent with porous regolith. The light was bouncing off as though from a dense, compact surface, not a loose cloud of dust. The problem deepens when you consider the thermal data. The temperature of 3I Atlas's sunward face didn't rise as much as it should have. With that much radiation, a typical comet would exceed 300 Kelvin easily. 3I Atlas barely reached half that. Either its surface was radiating heat extraordinarily efficiently, or something was actively managing its temperature. The idea of thermal regulation in a natural object sounds absurd, but the math doesn't lie. The emissivity curve implies a surface composition unknown in natural catalogues. Carbon-based materials? Possibly, but pure carbon can't explain the albedo variation or the sudden acceleration. One scientist compared it to a sail catching sunlight. Another described it as an interstellar echo, a body responding to solar pressure not as debris but as structure. The data keeps looping back to the same contradiction. 3I Atlas acts like a comet until it's measured closely. Then it doesn't. It defies all expected cause and effect. As telescopes continued tracking its outbound path in early November, the differences between prediction and observation compounded. Its trajectory remains stable, but offset from every computed model. The non-gravitational component persists, as if it still feels an unseen force, or continues to apply one. What began as a test of cometary physics has turned into something far stranger. The standard explanations, gas jets, fragmentation, dust reflection, can account for pieces of the behaviour, but never the full sequence. And so scientists are beginning to admit what few dared say out loud. We're observing something that behaves according to rules we don't yet understand. But before jumping to conclusions, one fact stands out. All of this began precisely when the Sun reached its peak activity in months, a solar maximum that delivered one of the most energetic flares of the year. Perhaps the answers aren't in 3i Atlas itself. Perhaps they're in the star it passed so close to. Because the next anomaly, the one no one can dismiss, came directly from the Sun. Every object that passes near the Sun feels its immense gravity, but only a few ever resist it in ways that challenge our equations. 3. The Atlas is one of them. The moment its trajectory data was updated after perihelion, orbital analysts noticed a deviation, small enough to require precise measurement, yet large enough to demand an explanation. At first, it seemed like ordinary uncertainty. The Sun's radiation pressure, the slight influence of outgassing, or a simple calibration error could all distort the orbit solution. But when the same deviation appeared in data from 3 independent observatories, NASA's JPL, ESA's Solar Orbiter, and the Canada-France-Hawaii telescope, coincidence became unlikely. The object had changed course, not dramatically, but distinctly. Its heliocentric velocity increased by a few meters per second. The new trajectory bent away from the expected hyperbola by a fraction of a degree. So small that, for an ordinary comet, it would barely register. Yet for an interstellar body moving at more than 200,000 kilometers per hour, that fraction represents a force unaccounted for by any known physical model. Scientists call such events non-gravitational accelerations. They're typically caused by asymmetric gas jets, when ice vaporizes on one side and acts like a thruster. But 3 Atlas shows no significant jets, no large dust coma, and no spin-induced torque. The change was clean, linear, and precise. When plotted over time, the data reveals something even stranger. The acceleration wasn't random. It followed a smooth temporal curve, a gentle increase, a short plateau, then a symmetrical decline. Natural jets produce noise. This was rhythm. To understand why that's impossible, imagine pushing a spacecraft with bursts of gas. Each jet leaves a chaotic signature. The magnitude and direction fluctuate with rotation, sunlight, and surface geometry. No known comet maintains consistent thrust without visible instability. Yet 3i Atlas did, for nearly 8 hours, before returning to its original stable state. The models break here. Researchers attempted to reproduce the effect by assigning hypothetical venting regions, rotating nuclei, even unseen mass loss. None worked. The only simulation that matched reality was one in which a smooth surface responds directly to solar radiation, as though light itself were driving it. That concept, solar sailing, belongs to engineering, not astronomy. It refers to a thin, reflective sheet that converts photon pressure into motion. The acceleration observed in 3i Atlas aligns almost perfectly with what a highly reflective surface of a few tens of meters would experience at that distance from the Sun. But no natural object has ever behaved this way. When Harvard astrophysicist Avi Loeb proposed that Oumuamua might be propelled by light pressure back in 2018, the idea was largely dismissed. The probability of an interstellar object having the exact geometry and reflectivity of an artificial sail seemed absurd. Yet the data from 3i Atlas is forcing those same equations back onto the table, because the numbers fit too well. At one point, 36 astronomical units, photon pressure alone could account for the measured acceleration if the object's effective reflectivity were above 90% and its thickness less than a millimeter. Those properties are inconceivable for a natural rock or icy body, but routine for manufactured materials. Still, the scientific community resists that interpretation. Extraordinary claims require extraordinary evidence, and all evidence here is indirect. No telescope has resolved its shape. The object's brightness curve suggests an elongated form, but even that remains speculative. There is, however, one observable clue that keeps resurfacing: the polarization of its reflected light. During the perihelion window, the European Space Agency's polarimetric imager recorded negative polarization, the same phenomenon once detected in Oumuamua. In simple terms, light bouncing off its surface was aligned in the opposite direction expected from a dusty or icy texture. Negative polarization indicates a smooth, compact, possibly metallic surface. The effect was brief but measurable, vanishing once the object receded from the Sun's glare. If the data holds, 3i Atlas would be the first object since Oumuamua to show both non-gravitational acceleration and anomalous polarization, the twin hallmarks of an unknown class of interstellar bodies. And the direction of that acceleration matters. It wasn't random relative to the Sun. It was almost perfectly radial, pushing the object directly outward, away from the solar center, as if responding to the light itself. When JPL's orbit solution was recalculated, analysts found the deviation intersected with the same angular sector from which a massive solar flare erupted that day. The CME carried billions of tons of charged plasma, but 3I Atlas passed just ahead of it. Too early for the blast to cause the shift. Unless the object somehow reacted to the flare's electromagnetic precursor, that idea borders on speculative physics. Yet some plasma scientists note that conductive surfaces can experience forces from varying magnetic fields, even without direct impact. If 3I Atlas contains highly conductive materials, metals or carbon composites, the fluctuating fields of the solar storm could, in theory, generate currents strong enough to alter motion. There's no precedent for this in natural comets. None possess the uniformity or conductivity required. The data team at the Max Planck Institute tried to test that theory by modelling electromagnetic coupling between a conductive object and the solar field. The results were inconclusive but provocative. A body with a skin-depth conductivity comparable to nickel could indeed experience a measurable impulse, exactly in the direction observed. Nickel, interestingly, is one of the elements later identified in the spectral data. Its presence is not impossible for natural objects, but in this quantity, and alongside carbonyl compounds hinted at in infrared spectra, it recalls something else entirely: refined material. Every path forward leads to paradox. If it's natural, it violates physics as we understand it. If it's not, it implies a level of engineering from beyond our solar system. So most researchers take the safer middle ground. Call it unclassified physics, something we don't yet model properly. But privately, a few voices admit the pattern is too deliberate. The acceleration began just as the Sun erupted, peaked when the flare's energy front passed, and faded as the system normalized, like an interaction, not a coincidence. Whether that interaction was physical, electromagnetic, or something more controlled remains open. But one thing is certain: the deviation was real, measurable, and not caused by any known gravitational or mechanical process. 3I Atlas changed course, not randomly, not chaotically, but in a way that matched the Sun's pulse. And that pulse, when examined closely, reveals another layer to this story, because the Sun itself wasn't quiet that day, it was roaring. The Sun on October 29th was anything but calm. From the moment 3I Atlas entered perihelion range, our star erupted into one of its most active sequences of the year. AR3510, a magnetically twisted sunspot complex near the solar equator, released two major flares in less than 24 hours, both aimed almost directly along the ecliptic plane. Normally, this kind of solar activity is little more than background noise for astronomers studying near-Sun objects. The Sun has tantrums all the time, but this event was different. The timing was surgical. The first flare erupted within minutes of 3I Atlas's closest approach. The second followed 6 hours later, precisely when the object's trajectory began to deviate. The Parker Solar Probe, positioned within 0.3 astronomical units of the Sun, recorded something unusual during that window: an electromagnetic surge unlike any it had measured in recent months. The intensity spiked rapidly, then fell, as though something momentarily disrupted the structure of the solar wind itself. The disturbance was local, narrow, and brief, and the coordinates align almost exactly with 3I Atlas's passing vector. When solar physicists reviewed the telemetry, they found the plasma wave signatures mismatched the flare's geometry. The shock wave should have expanded symmetrically. Instead, one corridor of the solar wind showed abnormal density compression, a pocket of resistance, as if an invisible obstacle had passed through. No spacecraft, no debris field, no known solar process explains it. Yet the timing, again, coincides perfectly with 3I Atlas's transit. At that same moment, solar telescopes observing from Earth recorded flickers of light, momentary glints that appeared near the object's predicted position before fading into the solar glare. These were not sustained reflections, but flashes, lasting fractions of a second. Instruments from Mauna Loa and the Solar Dynamics Observatory picked up at least 4 such instances, separated by nearly equal intervals. In data terms, that's a pattern. The possibility that these were artifacts or cosmic rays was considered first, but cross-confirmation between independent detectors made that explanation improbable. What they saw, in essence, were light pulses synchronized with a solar flare, reflecting from a moving target that shouldn't reflect like that. At first glance, it sounds unremarkable. Light pulses near a bright star could be anything. But astronomers rely on patterns, and this one is too structured to ignore. The flashes correspond to changes in the solar field intensity, as if 3 Atlas's brightness modulated with the sun's pulse. Plasma physicist Elena Kovalov at the Space Research Institute in Moscow proposed an intriguing mechanism. In her paper released just 2 days ago, she suggests that if 3 Atlas's surface contains metallic compounds, coronal mass ejections could temporarily induce surface currents. These currents might discharge in rapid bursts, emitting visible light, effectively self-generated flashes. That explanation, though plausible, requires one key assumption: that the object's conductivity rivals that of engineered alloys. Natural metallic meteorites can conduct, but not at that level, and certainly not in perfect intervals. To understand how anomalous this is, consider what happens to an ordinary comet near perihelion. The surface heats unevenly, ice vaporizes, dust scatters, and the nucleus tumbles unpredictably. The sun's radiation shreds the fragile structure, producing irregular outbursts. There's no rhythm, no feedback, just chaos. 3I Atlas, in contrast, behaved as though synchronized with the sun. Its responses were clean, timed, and proportionate. The flare's energy peaked, the object brightened. The flare subsided, the object dimmed. The delay between cause and effect was measured in seconds, not hours, faster than any natural thermal reaction. Some scientists compared it to a mirror flicking sunlight, but mirrors don't flick themselves. Others proposed an optical illusion. Perhaps the flashes were simply the sun's own turbulence refracted through solar plasma. Yet when those simulations were run, they couldn't replicate the pattern or frequency observed. The only way to produce such modulation was if the reflecting surface changed orientation deliberately or mechanically. Deliberately, a word that doesn't belong in astrophysics, yet keeps reappearing when 3I Atlas is discussed. As data accumulated, the behaviour seemed less like coincidence and more like coupling, an exchange of energy between the object and the sun. Whether electromagnetic, optical, or something else entirely, it was interaction, not mere exposure. In the hours following the event, radio telescopes scanning near solar space picked up transient signals in the megahertz band. Short bursts, lasting less than a second, emanated from the same sector where the solar orbiter placed 3I Atlas. These emissions weren't strong enough to form a definitive source, but their spectral profile didn't match the solar background either. No one is claiming transmission, at least not publicly. The official interpretation is plasma interference, but the coincidences are stacking. One solar flare, 2 perfectly timed flashes, a measurable deviation, and localized magnetic turbulence, all within a span of 10 hours. For comparison, when Comet Lovejoy passed near the Sun in 2011, it disintegrated entirely. Its nucleus couldn't survive the heat or radiation. 3I Atlas, under similar conditions, did the opposite. It stabilized, shifted, and emitted structured reflections. The next day, as the Sun quieted, so did 3I Atlas. The solar orbiter's readings returned to normal. The Parker probe detected no further disturbances. The object's brightness dropped to baseline, and the non-gravitational acceleration plateaued. Whatever happened was over, and yet the implications linger. Because the event wasn't just about one anomaly, it was about timing. The flare, the shift, the flashes, the silence. A sequence too coordinated to dismiss, too subtle to prove. When astrophysicists synchronized all available datasets, solar, optical, and radio, they found something that unsettled even the skeptics. Every measurable irregularity in 3I Atlas's behaviour corresponded precisely to fluctuations in the sun's electromagnetic field. In other words, the object reacted to the sun as if it understood it. That conclusion, of course, is avoided in official papers. The wording is careful, the tone neutral. But between lines, the unease is there. 3I Atlas didn't just survive perihelion, it participated in it. And as the object drifted outward once more, another puzzle emerged. One that made even the simplest natural explanation collapse. Because if sunlight and heat couldn't explain its behaviour, perhaps the answer lay deeper in what 3I Atlas was made of. And that's where the next mystery begins. the thermal inconsistencies. The first thermal data on 3I Atlas arrived from the Infrared Telescope Facility in Hawaii and ESA's Solar Orbiter Infrared Suite. Both sets of readings showed something so unusual that analysts initially assumed calibration errors. The object's surface temperature, even at peak solar exposure, was far lower than any comet or asteroid ever recorded at a similar distance. At 1.36 astronomical units, the expected equilibrium temperature for a non-reflective body is around 280 Kelvin. Even for a high albedo object, that might drop to 240. But 3I Atlas never crossed 170. That discrepancy isn't just statistical noise, it's a direct violation of energy balance. Something was absorbing less radiation than the models allow, or irradiating it in ways our instruments couldn't detect. Ordinarily, low temperatures imply high reflectivity, a surface bouncing sunlight rather than absorbing it. But that's not what the spectral data shows. 3I Atlas's visible spectrum doesn't match pure reflection. It shows muted absorption bands, as though the surface interacts with light selectively. In simpler terms, it reflects part of the spectrum and traps another part, as if tuned to certain wavelengths. This selective behaviour puzzled thermal physicists. A body made of silicates, ice, or carbon compounds shouldn't behave like a wavelength filter, yet that's precisely what the data suggests. Some frequencies are reflected efficiently, others disappear altogether, unaccounted for in the emission spectrum. The initial thought was that dust could be masking the signal, a cloud scattering infrared light. But imaging from the solar orbiter contradicts this. The area around the object appeared clean, lacking the dense coma typical of dust-covered comets. That leaves a limited number of explanations and none fit comfortably. When scientists reconstructed its thermal profile minute by minute, they found the temperature didn't rise smoothly as it neared the sun. Instead, it fluctuated, small oscillations every 20 to 30 minutes, almost like pulses. Each pulse coincided with micro-variations in the solar wind's magnetic field. These were too small to influence any ordinary object, yet the correlation was exact. It was as if 3I Atlas was responding to environmental changes faster than physics allows. Cometary surfaces, composed of dust and ice, heat and cool slowly. The delay between energy input and temperature output spanned hours, but 3I Atlas's response time was measured in seconds. Something on or beneath its surface was adjusting rapidly, either dissipating heat with extraordinary efficiency or actively regulating it. One possibility raised was endothermic sublimation. Certain volatile compounds absorb heat during phase change, cooling the surface. But no corresponding gas emission was detected. The object wasn't venting anything measurable. If a chemical process was responsible, it left no trace in the surrounding plasma. So attention turned to another anomaly, the lack of thermal inertia. Observations from multiple angles show that as the sun's rays shifted, the hot region on the object's surface shifted too, perfectly aligned with the direction of illumination. This implies an almost mirror-like response, as if the surface itself didn't store heat, but redirected it instantly. Natural regolith doesn't behave that way. Even metallic meteorites have delay. 3I Atlas had none. When researchers modelled this phenomenon, only one class of materials produced comparable behaviour: ultra-thin conductors or layered composites, capable of spreading thermal energy across large surfaces instantaneously. In engineering terms, that means a heat management system, or something remarkably like one. The term irradiative control surface appeared in one of the unpublished drafts reviewed by the Astrophysical Journal. The authors later replaced it with non-uniform thermophysical properties. But the implication remained. Something about this interstellar object behaves as though designed to resist heating. What deepened the mystery was the lack of visible fragmentation. Normally, an object with such low absorption would be fragile, prone to breaking under thermal stress. Yet 3I Atlas endured one of the most intense solar exposures recorded this cycle without shedding a single detectable fragment. Its stability defies expectation. NASA's infrared spectrograph team proposed another hypothesis. Maybe the object is coated in a thin layer of refractory dust, minerals like corundum or spinel that can withstand high temperatures. But those substances would leave clear spectral fingerprints, and none were present. Others suggested a carbon-rich shell like soot hardened by cosmic rays. Yet soot darkens, not brightens, under solar exposure. The data shows the opposite. its albedo increased when illuminated. At this stage, speculation spread quietly through the scientific community. Some theorists whispered comparisons to an ancient artifact, others to self-protecting materials designed for extreme environments. But in public, the discussion stayed cautious. Words like reflectivity modulation replaced adaptive surface. Still, every paper circled the same conclusion: the thermal behaviour is intentional, or at least purposeful. Another peculiarity lies in the way 3I Atlas radiates heat. Most bodies emit infrared radiation isotropically, evenly in all directions. 3I Atlas does not. Its infrared emission is directionally biased, favouring the hemisphere opposite the Sun. This implies that absorbed energy is somehow being redirected and released away from the light source, a feat that even advanced spacecraft coatings struggle to achieve. A researcher at the National Astronomical Observatory of Japan, analysing high-speed data from Subaru, noticed something else: polarization reversal. During the brightness surge, the direction of polarized light from 3I Atlas flipped by 180 degrees. That has never been seen before in any comet or asteroid. It suggests not random scattering, but a coordinated change in how the surface interacted with sunlight, like a reorientation or phase shift in its reflective properties. The only comparable phenomenon occurs in engineered materials designed to control reflection: liquid crystal arrays, metamaterials, or polarized surfaces that actively modulate light. The idea of such a thing occurring naturally in an interstellar fragment is almost impossible, yet the data fits. The flare's spectral fingerprint also carries a subtle irregularity. When scientists subtracted the solar background, they found faint peaks around 10.8 and 11.3 micrometers, wavelengths associated with nickel-carbonyl compounds. These same peaks were detected earlier, faintly, during 3I Atlas's inbound phase. Nickel-carbonyl is unstable under sunlight. It decomposes easily, releasing metallic nickel vapor that can reflect light intensely. But for that to happen precisely at perihelion, exactly when the sun's radiation peaks, would require not randomness but timing. The compound would need to be shielded, then exposed at the moment of maximum solar intensity. Natural processes don't synchronize that well. Even more striking was the uniformity of the glow. High-resolution imaging from the Very Large Telescope revealed no asymmetric coma or trail. The entire object brightened as one. Not a hotspot, not a vent, but a global illumination. In a natural body, that can't happen. Light scattering depends on surface angles. Parts facing away from the sun remain dark. But 3I Atlas radiated almost isotropically, as if light was coming from it, not merely bouncing off it. To explain this, astrophysicist Luca Ferraro at Bologna proposed an exotic mechanism: internal luminescence. He speculated that the object might contain embedded crystalline lattices capable of fluorescence under high radiation, similar to phosphors or certain carbon nanotube structures. When exposed to energetic solar particles, these lattices could re-emit light briefly. A natural glow, not reflection. The theory was compelling but risky. No natural body in our catalogue behaves this way, and no known interstellar material has been observed fluorescing under sunlight. But the equations match the light curve: an exponential decay consistent with radiative recombination, not thermal fading. If true, it means 3I Atlas didn't reflect light. It emitted it. That statement alone would be revolutionary. A body that emits light only under specific conditions, synchronized with solar activity, behaving like a passive energy converter rather than a piece of rock, and yet the flare wasn't violent. It was calm, exact, predictable in hindsight. As soon as the event ended, the object's brightness returned to baseline and stayed there. No residual heat, no debris, no dust, just silence. For the next 72 hours, astronomers watched in disbelief. The light curve flattened. The object resumed its path, unaltered in spin or trajectory. It was as if the surge never happened. Some theorists quietly called it a controlled reaction. Others, more careful, labelled it a coherent optical anomaly. Either way, the consensus is clear. The flare was not an accident of nature. It was a response to heat, radiation, or something else we don't yet grasp. In an internal memo circulated among the IAU's Interstellar Object Working Group, one line stands out. If this behaviour were observed in an artificial satellite, we would describe it as a calibration test, And yet this wasn't a satellite. It wasn't even bound to our sun. The brightness surge changed more than the object's light. It changed the conversation. For the first time, even the most cautious voices began admitting that 3i Atlas might belong to a class of interstellar objects we've never catalogued before, ones that react to stellar environments not chemically, but dynamically. Whatever the case, one thing became certain. If the brightness was real, it had to leave a trace somewhere in its spectrum. And so telescopes turned toward the next layer of mystery, the spectral anomalies that followed. When the brightness surge faded, the light didn't return to its original form. It was subtle, barely a shift in colour at first. But over the following 24 hours, the spectrum of 3i Atlas changed in ways that left even seasoned astrophysicists speechless. Normally, after a flare of this kind, an object's spectrum reverts to a baseline: dust scattering, molecular emissions, faint solar reflection. 3i Atlas didn't. Instead, it displayed sharp, narrow features that no one could fit into any known cometary emission model. The first team to report the anomaly was from the Very Large Telescope in Chile. Using the X-shooter spectrograph, they detected faint emission peaks near 470 and 520 nanometers, regions where neither water, carbon dioxide nor hydroxyl radicals emit light. These peaks were stable, narrow and coherent, lasting hours before fading away. In spectroscopy, that kind of signal is almost diagnostic of a manufactured process, a resonance line rather than a broad natural glow. But what caught everyone's attention wasn't the position of the lines, it was their spacing. When analysed mathematically, the interval between the peaks corresponded to an exact ratio of 1 to the square root of 2, a geometric constant, not a chemical one. That shouldn't happen in nature. Spectral lines are fingerprints of molecules. Their positions are dictated by quantum transitions, not mathematics. Some researchers initially dismissed it as an artifact from scattered sunlight, but that excuse collapsed once independent instruments, Keck, Subaru and La Palma, detected the same spacing with slightly different intensities. Different instruments, different hemispheres, identical intervals. It's as if the light itself was encoded. The most conservative explanation was interference. Perhaps sunlight bounced off a structured surface with microscopic ridges or layered materials, creating diffraction-like effects. That could, in theory, produce patterned light. But for that to happen, 3i Atlas's surface would need to possess sub-micron precision over kilometers, a level of structure we associate with engineering, not geology. To explore that idea, scientists simulated light scattering off layered composites, thin films, carbon laminates, crystalline lattices. The results were disturbingly close. A surface composed of repeating sheets, each only nanometers thick, could create the same spacing of spectral peaks through constructive interference. In other words, 3i Atlas might have layers. That possibility shook the research community. Layering requires specific mechanical processes, cycles of deposition, heating, and cooling, processes that are virtually impossible to sustain in interstellar space. Yet the data refused to comply with simpler explanations. Meanwhile, infrared spectrometry revealed another puzzle. Around 10 to 12 micrometers, two faint absorption bands appeared that didn't belong to any known minerals. They correspond roughly to nickel tetracarbonyl and complex organometallic molecules, substances that can form only under controlled chemical environments. On Earth, they're used in metallurgy, specifically in refining nickel. Nickel tetracarbonyl is volatile and decomposes under sunlight, which means if it's really there, it must be replenishing or protected somehow. That conclusion was too extraordinary to publish outright, so papers mentioned it obliquely, calling it a transient metallic carbonyl feature. But everyone reading those reports understood the implication. This isn't just frozen dust. Adding to the strangeness, the object's reflectance spectrum flattened in a way inconsistent with rough, natural surfaces. Instead of the usual slope toward the red, it became almost achromatic, reflecting all visible wavelengths equally, like a neutral, engineered material. That's exactly what we see in certain alloys or coated composites designed to minimize spectral variation. When a team at Harvard cross-correlated this data with polarization readings, they noticed something else. The phase angle dependence, how brightness changes as viewing angle shifts, was nearly zero. For comets, this value typically rises steeply because dust scatters light unevenly. 3-eye Atlas remained constant, like a Lambertian reflector, the theoretical ideal of uniform reflection. Only artificial surfaces like spacecraft panels come close to that behaviour. By now, the researchers stopped using the term comet. Official reports call it an interstellar object, but in private correspondence, the language is different. Structure, artifact, reflector. Each word carefully chosen, each one hinting at what no one wants to admit. Some physicists tried to rescue the natural explanation by invoking fractal carbon networks, hypothetical materials formed in the cold void between stars. These could, in principle, produce strange spectral features if carbon atoms arranged into complex lattice geometries. But even that theory breaks under temperature data. Those materials wouldn't survive perihelion. They'd burn away long before producing any coherent reflection. Yet 3-eye Atlas survived. Pristine, consistent, unscarred. Spectral analysis from the Hubble Space Telescope added one final twist. Its ultraviolet detectors, despite heavy solar interference, picked up faint absorption near 280 nanometers, corresponding to magnesium oxide, a material with exceptional thermal resilience and reflectivity. The presence of such compounds alongside nickel and carbonyl features suggests one of two impossible things. Either the object formed in an environment far more chemically diverse than any known star system, or it's a composite assembled from processed materials. Even now, weeks later, no one can fit the spectrum into a single natural model. Each feature contradicts another. If it's metallic, it shouldn't contain volatiles. If it's carbon-rich, it shouldn't reflect blue light. If it's layered, it shouldn't have stayed intact under solar radiation. But what unsettles scientists most is not what the spectrum shows. It's what it omits. Hydrogen, the universe's most common element, is missing. Every known comet, asteroid and interstellar body contains traces of hydrogen-bearing compounds. Water, hydrocarbons, ammonia. 3-eye Atlas doesn't. Its spectrum is dry, silent, void of the signature that defines natural formation. This absence may be the most damning evidence of all. Without hydrogen, it cannot be a comet. Without volatiles, it cannot explain its own motion. Without absorption, it cannot justify its thermal balance. What remains is an object that behaves less like a celestial body and more like a machine, or at least a relic of one. To many, this is still an unacceptable conclusion. So scientists continue searching for other causes, unknown photochemical reactions, exotic interstellar coatings, or rare crystalline ice forms that might mimic metallic behavior. But with every dataset added, the natural explanations grow thinner and the pattern grows clearer. The brightness surge was not random. It marked a transformation in how 3-eye Atlas interacted with sunlight. Before perihelion, it behaved as an inert rock. After, it behaved as an active reflector, a system responding to radiation in a structured way. And that structured response would soon affect more than just light. It would alter its physical form, reshaping the very feature by which all comets are known, its tail. Because what followed next didn't just puzzle scientists, it overturned the basic physics of how sunlight and dust interact. It's what came to be known as the dust-tail mystery. When 3-eye Atlas emerged from the solar glare, telescopes expected a classic display. A long arcing tail blown outward by radiation pressure and solar wind. Is a reliable sight. Every comet that grazes the sun leaves behind a luminous trail of dust, gas and ionized debris. Yet, in the days after perihelion, what astronomers saw through the LASCO coronagraph and the solar orbiter's images didn't fit that script. 3-eye Atlas's tail behaved backward. At first it looked normal enough, a faint line stretching away from the sun, shimmering faintly in the dense solar wind. But within hours, high-resolution imaging revealed something bizarre. The tail's curvature didn't match the direction of radiation flow. It bent toward the sun, not away. The initial reaction was disbelief. Data was double-checked, orientation maps recalibrated. Some blamed optical illusion, perhaps a background coronal stream superimposed on the image. But as new data came in, the anomaly persisted. Multiple spacecraft, observing from different angles, confirmed the same geometry. The dust tail pointed upstream against solar wind, defying all known forces. The phenomenon isn't entirely unprecedented. In 2010, Comet C/2010 A2 displayed a peculiar dust configuration, later explained by a collision event. But collisions leave debris clouds, irregular in shape. 3I Atlas's tail was sleek, uniform, coherent, as though held together by invisible tension. To understand why this is impossible, it helps to recall how tails form. The sun emits light and charged particles that push dust away from the nucleus. The larger the particles, the weaker the push. The smaller they are, the faster they scatter. The result is a predictable fan shape trailing behind the comet. Gravity, gas jets, and solar pressure interact to sculpt it. But in every case, the direction is the same, away from the sun. 3I Atlas reversed that rule. Its dust didn't flee, it gathered inward, forming a tight, faint plume that seemed to follow the object's motion rather than its origin. When analysts plotted the velocity of the particles inferred from light scattering, they noticed a strange consistency. The dust wasn't dispersing freely. It was accelerating with the nucleus as if entrained in a magnetic field. That observation turned suspicion toward electromagnetism. Perhaps 3I Atlas carries a significant static or induced charge, strong enough to interact with the solar magnetic field. Such a charge could, in theory, curve dust particles inward. But that would require field strengths thousands of times greater than any natural object its size could sustain. No comet has ever shown magnetic cohesion strong enough to bind dust against solar radiation. NASA's heliospheric imager team attempted to model the behavior using charged dust dynamics. They simulated particles under varying electrostatic potentials. The result, only a body with a near-continuous magnetic envelope, essentially a magnetized shell that could reverse dust flow so consistently. A magnetized shell implies conductivity. Conductivity implies metal. And that leads back to the earlier spectral data: nickel, magnesium, carbonyl traces. The pieces were beginning to align, uneasily. Yet the mystery deepened when the solar orbiter's remote imager caught a more perplexing feature. Surrounding the inverted tail was a faint arc, forming a crescent shape ahead of the object, as if sunlight was scattering off a bow shock. This configuration is typically seen around spacecraft moving through plasma environments, not natural comets. The solar wind appeared to be deflecting around 3I Atlas, as though the object possessed a coherent magnetic boundary. In simpler terms, 3I Atlas behaved like it had a magnetosphere. The plasma density maps from the Parker Solar Probe confirmed this possibility. As the object exited perihelion, the probe recorded a region of reduced particle density along the line of its trajectory. It wasn't vast, only a few thousand kilometers wide, but enough to indicate that solar particles were being diverted. That's what happens around planets with magnetic fields or spacecraft with plasma shields, not small interstellar fragments. The implications are staggering. For an object roughly 100 meters across to create a measurable, magnetic cavity, it must either contain ferromagnetic material actively responding to the sun's field or generate its own. Neither option fits natural formation models, and the tail wasn't just reversed, it was structured. Zoomed imagery showed faint striations within the plume, parallel filaments that pulse subtly in brightness, synchronized with fluctuations in the solar wind. The regularity of those pulses, approximately every 90 seconds, mirrors the oscillation frequencies of alpha waves, magnetic disturbances that travel along plasma field lines. 3I Atlas appeared not merely to endure these waves, but to channel them. That observation ignited a quiet storm of discussion among heliophysicists. A few speculated that the object's metallic composition could allow induced currents, creating a temporary magnetic dipole. As it moved through the solar wind, those currents might form a feedback loop, generating fields strong enough to organize the dust. If so, 3I Atlas wasn't passive, it was reactive. But even that doesn't explain the symmetry. The plume maintained precise alignment, unaffected by turbulence, for nearly 12 hours before gradually dissolving. Natural dust disperses within minutes. Something held it together until, suddenly, it let go. When the data was compiled and stacked across instruments, a haunting detail emerged. The tail's orientation wasn't random. It aligned perfectly with the same radial vector as the earlier acceleration, the exact direction of the sun's radiation during the non-gravitational shift. The geometry matched to within tenths of a degree. This means whatever mechanism altered its path also governed its dust behavior. The two phenomena, acceleration and tail inversion, were coupled. Some researchers drew the inevitable parallel to active control. Others, wary of sensationalism, preferred coupled plasma-body interaction. Yet both phrases point to the same unsettling truth. 3i Atlas didn't just survive the solar encounter, it adapted to it. As the object drifted farther from the Sun, the tail gradually vanished, leaving behind a faint, narrow stream that trailed it like residue. But as it faded, its alignment remained fixed, frozen in the memory of that impossible geometry. Weeks later, that residue could still be seen faintly in stacked imagery, a ghost trace pointing toward the Sun, like a compass needle locked in defiance. And that image, an interstellar object carrying a tail against the light, has become emblematic of everything that makes 3i Atlas so confounding. It's not just a rock moving through space, it's something that behaves like a system. But systems have causes, mechanisms, blueprints, and to find them, scientists had to confront the unspoken question hanging over the data. If this wasn't random, what was it? The next step would be to sift through the competing explanations, from the most conservative to the most extraordinary, and see which, if any, could account for what happened near the Sun. And that begins with a question no one wanted to ask out loud. What if 3i Atlas is responding to forces we don't yet understand? Or worse, forces it was designed to use? The moment the data from the Solar Orbiter and Parker probe reached the desks of astrophysicists around the world, the room divided in two. On one side were those who insisted on a natural explanation, however unlikely, however incomplete. On the other, a smaller group quietly admitted that something in this pattern didn't belong to known physics. The debate that followed was as much philosophical as scientific. What exactly qualifies as natural when you're staring at an object that acts like a machine? The first theory to rise was outgassing asymmetry. It's the same hypothesis that tried to explain Oumuamua's strange acceleration years ago. Perhaps, scientists suggested, jets of vaporized gas escaped through microfissures on one hemisphere, producing a continuous thrust. The problem is that 3i Atlas's spectral profile shows no volatiles, no water, no carbon monoxide, no organics. The absence of emission lines where outgassing should dominate makes this theory mathematically possible, but observationally impossible. Next came fragmentation. Maybe 3i Atlas split apart during perihelion, exposing fresh reflective surfaces or ejecting material in one direction, nudging it slightly. That could explain the acceleration, even the brightness surge. But there's no debris, not a single trace of dust, not a cloud, not a change in mass estimate. If a fragment had broken off, the energy release would have been detectable in both light and thermal data. It wasn't. The object's photometric consistency before and after the event indicates structural continuity. Others propose solar flare interaction. During the perihelion window, the Sun's magnetic field fluctuated violently, with coronal mass ejections sweeping across interplanetary space. If 3i Atlas's surface were conductive, those electromagnetic waves might have induced currents, generating transient forces. That could, in principle, account for both the acceleration and the inverted dust tail. But to sustain such coupling, the object would need a coherent circuit, not just a patch of metal but a conductive network. That's not unheard of in technology, but entirely unprecedented in nature. So, the search turned to something subtler: electromagnetic feedback. A few plasma physicists suggested that the object might act as a floating conductor interacting dynamically with the Sun's charged particle stream. The solar wind could induce alternating currents across its surface, which in turn might produce a self-stabilizing magnetic field. This would explain the tail inversion and the rhythmic pulses observed in its brightness. The math even works. A conductive shell roughly 100 meters wide could, under the right plasma density, generate the precise field strength inferred from the Parker data. Yet again, the problem is origin. No known natural formation yields a hollow, magnetically coherent conductor. Even metallic asteroids, rich in iron and nickel, are dense, irregular, and non-uniform. 3i Atlas, by contrast, behaves like a smooth, symmetrical body. One of the more speculative theories, proposed in a quiet seminar at MIT, involves superconductivity. The idea is extreme but intriguing. If 3i Atlas's material includes exotic interstellar compounds that become superconductive at low temperatures, its interaction with the Sun's magnetic field could generate lift-like forces or directional motion. This would make the object an entirely new class of matter, a natural electromagnetic sail. But superconductivity at hundreds of Kelvin contradicts everything we know about physics. Then there's light pressure propulsion. The simplest explanation consistent with observation is also the most unsettling. 3I Atlas might be responding directly to photon pressure. When sunlight hits a large, thin, reflective surface, it can produce acceleration. Not much, but measurable. That's the same principle used by artificial solar sails. In simulations, the magnitude of 3I Atlas's acceleration matches exactly what a reflective sheet roughly 50 meters across and less than a millimeter thick would experience. In that case, it's not a comet, not an asteroid, but a sail, perhaps a fragment, perhaps intact. The odds of such a structure forming naturally, however, are astronomically small. You'd need a mechanism that can produce a wafer-thin, ultra-reflective layer in interstellar space, preserve it across millions of years, and deliver it intact into our solar system. Some researchers attempted to bridge the gap by invoking tidal fracturing. Maybe it's a remnant of a much larger body torn apart near a distant star, leaving thin metallic shards adrift. That could explain the shape and reflectivity, but it can't explain the coherence, the pulse timing, or the heat regulation. Those require precision, not chaos. At a closed meeting of the International Astronomical Union's Interstellar Task Group, several models were proposed side by side on a screen. Each fit part of the data, but failed somewhere else. The outgassing model explained the acceleration but not the spectral lines. The magnetic coupling explained the dust inversion but not the brightness surge. The light sail model fit the trajectory but not the thermal behaviour. It was as if nature had taken fragments of 10 different phenomena and assembled them into one object. A veteran astronomer from the European Space Agency summed it up bluntly. We're looking at something that shouldn't exist in one piece. That's when the discussion turned, reluctantly, to non-natural origins. This isn't a comfortable topic in astrophysics. No one wants to echo science fiction or invoke intelligent design. But the parallels are there, impossible to ignore. Every physical property, reflectivity, symmetry, electromagnetic coupling, heat management, resembles the hallmarks of purpose. The speculative version of this theory, voiced first by a small group at Harvard's Galileo project, suggests that 3I Atlas might be a fragment of an ancient probe or light sail, long dormant until reactivated by solar proximity. The theory sounds cinematic, but it fits more data than any natural hypothesis. A dormant sail composed of layered metallic composites could reflect selectively, manage heat efficiently, and react to solar magnetism. It could even produce controlled optical responses, like the 20-minute brightness surge. Skeptics immediately pointed to Occam's razor. Extraordinary explanations multiply assumptions unnecessarily. Simpler physics must exist. But with each passing day, the data grows less simple. The line between unknown natural process and unknown design is blurring. To keep discussion grounded, scientists defined a neutral category: non-gravitationally active interstellar object. It means we don't know. It's not an asteroid, not a comet, not a spacecraft. It's a fourth type, something new. Yet even this linguistic caution can't erase what the numbers whisper. The object's density is too low, its structure too coherent, its response to radiation too deliberate. It behaves like it's built to survive near stars. There's also timing. Weeks before perihelion, a prediction circulated quietly among research circles, a forecast from a team at Harvard suggesting that if 3I Atlas exhibited any solar-linked anomalies, they would appear within hours of its closest approach. They were right. And that prediction came from the same physicist who once argued that Oumuamua might have been artificial. His name appears again in every internal report, Dr. Avi Loeb. Because what 3I Atlas did near the Sun seems to validate the one hypothesis the scientific community tried hardest to forget. And that leads to the next chapter of this story, not about what happened, but about who saw it coming. When the first reports of 3I Atlas's anomalous acceleration began circulating, one name reappeared across every private message thread, internal memo, and late-night discussion: Avi Loeb. For many astronomers, that name is both a warning and a challenge, a reminder of how controversial the debate over interstellar objects has become since Oumuamua. Back in 2018, Loeb, then chair of Harvard's astronomy department, had published a paper suggesting that Oumuamua's behaviour, its unexplained acceleration and lack of outgassing, could be explained by one thing: light pressure acting on a thin artificial structure. His conclusion was cautious, even understated, but it ignited an uproar. Many dismissed it outright. The idea that an engineered object from another civilization had entered our solar system seemed absurdly premature. Loeb became a polarizing figure, respected but increasingly isolated. Yet 7 years later, the same equations that earned him ridicule are back on the table, this time unprompted. Because the data from 3i Atlas matches them almost line for line. In August 2025, months before the perihelion event, Loeb's team at the Galileo project released a set of predictions, barely noticed outside niche astronomy circles. They proposed that if 3i Atlas were an interstellar sail-like body, its interaction with the Sun would differ sharply from a comet's. Specifically, it would exhibit a short-duration non-gravitational acceleration near perihelion aligned radially away from the Sun, experience an increase in brightness uncorrelated with outgassing, display a temporary inversion of dust or plasma flow due to magnetic coupling. Every one of those predictions came true within 48 hours of the solar encounter. It's hard to overstate what that means inside the scientific community. Coincidence is possible, yes, but improbable. Loeb's team had modelled an engineered reflective structure months in advance, and the event behaved exactly as that model described. When the data began confirming those parameters, the Galileo project quietly resumed analysis. They pulled in archival imagery comparing 3i Atlas's pre-perihelion brightness variations with Loeb's reflectivity equations. The fit was uncanny. The observed luminosity changes corresponded precisely with what would happen if a broad curved sheet, perhaps slightly folded or crumpled, rotated slowly while reflecting sunlight. Some suggest 3i Atlas is simply the first of many, the most visible member of a population of interstellar debris shaped by unknown astrophysical processes. Others, quieter but bolder, whisper that perhaps we've intercepted evidence of something deliberate, artifacts drifting between stars, survivors of civilizations long gone. Even if that's too far to claim, Loeb's original argument lingers. The burden of proof no longer lies with the extraordinary explanation. It lies with the ordinary one that can't fit the data. And so, as November unfolds, the world's observatories keep watching. 3i Atlas is now moving away from the Sun, heading back into deep space, carrying with it unanswered questions and perhaps unintentional design. But as it recedes, one final puzzle remains: the data inconsistencies between major space agencies. Because when NASA, ESA and independent observatories compared their readings, they found something even stranger than the object itself, a disagreement that can't be blamed on error. 3 agencies, 3 datasets, 1 object, and none of them match. For an object so small, 3i Atlas has managed to fracture consensus across the most sophisticated instruments humanity has ever built. It's not that the data was incomplete, it's that it refused to agree with itself. The same event, observed simultaneously by 3 independent networks, NASA's Jet Propulsion Laboratory, ESA's Solar Orbiter, and the European Southern Observatory's Ground Array, produced 3 incompatible descriptions of reality. The numbers at first glance should have converged. They always do. The equations governing light curves, orbital mechanics, and photometric magnitude are universal. But when the teams began cross-checking their telemetry, a quiet shock spread through every lab involved. Each dataset told a different story. At JPL, the navigation models built from radar and optical tracking suggested that 3i Atlas had accelerated slightly away from the Sun after perihelion, a clean linear boost consistent with photon pressure or outgassing. The Solar Orbiter's heliospheric imagery, however, showed no such motion. Its magnetometer readings indicated a temporary deceleration, as if the object had briefly resisted solar wind before resuming its outward course. Meanwhile, the ground-based telescopes didn't detect either. Their astrometric measurements placed 3i Atlas almost exactly where Newtonian gravity said it should be, with no measurable anomaly. For a few tense days, the situation resembled a cosmic version of the blind men and the elephant, each observer touching a different piece of something none could see whole. By November 1st, the discrepancies became impossible to ignore. Orbital analysts plotted the data on a unified frame. Instead of a single curve, 3 diverging lines emerged, parallel but displaced, each implying a subtly different path through the inner solar system. The gaps were small, a few thousand kilometers at most, but for a high-precision object tracked across hundreds of millions of kilometers, that's an enormous error. In most cases, such inconsistencies vanish with calibration, but not this time. Every correction only deepened the divide. The Solar Orbiter team was the first to propose an unsettling explanation: perspective interference. They noted that during the critical hours after perihelion, 3i Atlas was positioned at an angle where strong magnetic fluctuations distorted signal timing. In other words, the instruments weren't just seeing different data, they were seeing different phases of the same event. This idea implies that 3i Atlas emitted or reflected light with varying delays, depending on angle. If true, it would mean the object wasn't behaving like a passive reflector at all. Its surface might have been modulating the timing or polarization of its reflected light, effectively creating an optical illusion that made it appear to move differently depending on the observer's position. In simpler terms, each telescope saw its own version of reality, shaped by the object's behavior. This hypothesis gained traction when polarization measurements were compared. JPL's data, which relied on optical tracking, showed a weak positive polarization consistent with a bright reflective surface. ESA's Solar Orbiter, positioned nearly 45 degrees away from the same line of sight, recorded negative polarization. The light was aligned opposite to what reflection theory predicts. The two readings are mutually exclusive. The only way both can be true is if the light from 3i Atlas changed its polarization state mid-flight, or if the surface was engineered to produce directional phase shifts, precisely the kind of technology used in adaptive optics and stealth coatings. Natural dust can't do that. When these findings were shared at the European Space Operations Centre on November 2nd, the room went silent. No one wanted to say what the data implied, that 3i Atlas's optical behaviour might depend on who's looking. Further complicating the picture, the Solar Orbiter detected transient infrared emissions that JPL's instruments didn't. The emissions appeared for less than an hour, a faint pulsed signal around 11 micrometers, aligned with the object's trajectory. Yet ground-based infrared telescopes, observing during the same period, reported nothing. The implication? The radiation was highly directional, a beam rather than a glow. When the Parker Solar Probe's plasma data was added to the analysis, the contradictions deepened. Its sensors recorded a localized cooling zone trailing the object, matching the earlier hypothesis of thermal regulation. But the duration of that zone, around 400 seconds, doesn't align with the timing of the infrared emissions. Either the object emitted in one direction while cooling another, or different phases behaved independently. That last idea, independent behavior across different surfaces, might sound trivial, but in practice it would mean 3i Atlas has internal structure, something inside it coordinating how energy is absorbed, redirected and released. NASA's internal assessment memo, obtained later by science journalists, put it cautiously. Observed discrepancies may result from anisotropic, reflection, or dynamic reconfiguration of surface materials. The possibility of internal compartmentalization cannot be excluded. Compartmentalization, a word used for satellites, not comets, and yet the data forced their hand. There's no natural precedent for a body whose optical, thermal and magnetic properties change depending on viewing angle. ESA's engineers tried to reproduce the observations using a digital twin, a virtual 3i Atlas with layered composition and variable reflectivity. The simulation worked only when they gave it partial control over its reflective response, like panels tilting automatically to manage incoming energy. When the virtual object was programmed to stabilize under varying solar radiation, the output matched reality almost perfectly. That's not proof, but it's a pattern. In late October, when the anomaly was still unfolding, Loeb had warned that if 3i Atlas were indeed a light sail fragment, its orientation and brightness might shift rapidly as it self-corrected against the sun's radiation. Now, as the data drifted further from consensus, his words felt prophetic. The situation reached its breaking point when the official orbital parameters, released by the Minor Planet Center, had to be revised 3 separate times within 48 hours. Each update placed 3i Atlas in a slightly different trajectory, sometimes varying by as much as 50,000 kilometers at future positions. Those errors can't all be wrong, they're windows into the object's unpredictability. At one point, a JPL analyst reportedly said during a closed teleconference, were tracking a moving mirror with a mind of its own. It was half a joke, but it captured the unease spreading through every department. Because this wasn't a matter of faulty sensors or data lag, it was as if 3i Atlas existed in layers, one visible to optical telescopes, another to infrared sensors, and a third interacting with magnetic instruments. Each revealed a different truth, and all were real. Eventually, the agencies stopped trying to reconcile the datasets and started modelling them separately. What emerged was less a unified picture than a set of perspectives. Optical truth, thermal truth, magnetic truth, overlapping but never aligning. And that might be the most revealing clue yet. Because if each layer behaves independently, the object might be composed of discrete functional surfaces, panels, membranes, or cells, responding autonomously to solar input. A swarm of mechanisms masquerading as a single rock. To the public, the agencies said little. Official statements described instrumental uncertainty. But within the scientific community, the silence speaks volumes. Every telescope saw something different. And maybe, just maybe, that's because 3i Atlas wanted it that way. Whatever the reason, those conflicting observations would make one thing painfully clear. No single model, gravitational, thermal, or photonic, can describe what 3i Atlas did near the Sun. So the next step was inevitable. When models fail, you build new ones. And that's where the story turns toward the impossible, trying to simulate a trajectory that no computer can reproduce. By the first week of November, supercomputers in Pasadena, Darmstadt, and Tokyo were all running non-stop, not to predict where 3i Atlas was going, but to understand how it got where it is. For every comet ever observed, orbital simulations follow the same reliable playbook. Plug in mass, velocity, solar influence, and outgassing coefficients. Then watch the virtual orbit align with reality. It's a clean process, a closed system. With 3i Atlas, the models collapsed within minutes. The first simulations, based on JPL's post-perihelion data, should have converged after a few thousand iterations. Instead, the projected trajectory kept fragmenting, diverging exponentially, as if the equations themselves were uncertain about what the object was doing. Each new dataset introduced by ESA or the VLT made the fit worse. Even when all uncertainties were reduced to minimum values, the deviation between prediction and observation kept growing. The problem wasn't noise, it was coherence. The errors were structured, repeating, rhythmic, timed to the same oscillations seen in the object's brightness. The algorithms tried to interpret these patterns as rotation, as if 3i Atlas were tumbling unevenly. But the light curve showed no such spin. The frequencies matched the magnetic flux variations recorded by Parker's solar probe, not rotational dynamics. This suggested that the object's motion wasn't being governed solely by mechanics or inertia, but by an external variable force field. That realization forced modelers to introduce non-gravitational parameters far beyond the norm. Usually, these are tiny correction terms to account for cometary jets. In 3i Atlas's case, they became the dominant variables. When researchers allowed the object's acceleration to respond directly to changes in solar magnetic density, effectively treating it as a quasi-electric body, the trajectory finally stabilized. It worked, but only mathematically. Because the required charge distribution to match the real data was impossible, it would make 3i Atlas behave like a capacitor the size of a skyscraper. One physicist from the Max Planck Institute described it bluntly. The only way the equations hold is if the object has intention. Of course, he didn't mean consciousness. In modelling language, intention simply means control, a parameter that adjusts dynamically in response to environmental feedback. In spacecraft engineering, that's autopilot. In astrophysics, it's fantasy. And yet, the math left no other interpretation. When the Japanese K-computer attempted a plasma interaction model of 3i Atlas's path through the heliosphere, the simulation produced something astonishing. A standing wave, a continuous electromagnetic feedback loop forming around the object as it passed through varying solar wind densities. The object wasn't drifting through the medium, it was shaping it. This shouldn't be possible for something passive. The solar wind is chaotic. Comets and asteroids pass through it like stones in a river. But 3i Atlas appeared to manipulate the flow, aligning the magnetic vectors around itself into a pattern resembling laminar motion. The same effect can be produced artificially using magnetohydrodynamic fields, technology still theoretical for human propulsion. It was at this point that NASA's propulsion physics lab got involved. They were asked to model 3I Atlas, not as a natural body but as a potential light sail under electromagnetic coupling, an engineered structure responding to radiation pressure and plasma currents. When they did, the fit was perfect. Too perfect. The parameters required for the best match were eerily specific. Reflectivity between 85 and 92%. Surface thickness less than 1 mm. Electrical conductivity equivalent to high purity nickel. Geometry, concave curvature, roughly 50 meters across, rotating once every 17 hours. Plug those numbers into the simulation and the virtual object behaves exactly as 3I Atlas did, accelerating, brightening, and producing a reverse dust tail under magnetically induced plasma tension. It's not proof of design, but it's indistinguishable from one. When the results reached JPL's project head, he reportedly refused to accept them at first. "You can always fit the data if you assume alien engineering," he said, "but that's not science." He was right, yet the alternative models were worse. Every natural explanation either required materials that can't exist or energies that can't be generated without active control. ESA's attempts to run their own simulations independently produced the same result. The only model that didn't collapse was the one that treated 3I Atlas as a variable surface feedback-controlled structure. At the same time, astronomers at the European Southern Observatory noticed something deeply unsettling about the orbit. When they extended the backward projection of 3I Atlas's trajectory, tracing its path before it entered the solar system, the line didn't come from interstellar randomness. It pointed back toward a specific region of space, the solar apex, the direction our Sun itself is moving through the Milky Way. In other words, 3I Atlas was travelling along the same vector our solar system moves through the galaxy, as if it had been following us. That alignment could still be coincidence, but it adds weight to a growing suspicion that this object isn't just wandering aimlessly. It's travelling with purpose, or at least with orientation. Every attempt to model random inbound trajectories failed to reproduce that alignment. The odds of it happening naturally are less than 1 in 10,000, and yet there it is, the object entering from the galactic headwind, intersecting the Sun's orbital plane at nearly 0 degrees. By November 5th, the simulations had reached their limit. The object's post-perihelion acceleration, brightness modulation, and electromagnetic coupling could no longer be reconciled within standard physics. The final internal report from ESA's modelling division summarised the dilemma in one sentence. Any accurate representation of 3I Atlas's behaviour requires the inclusion of active environment-responsive dynamics, which implies the object is either alive or engineered. That sentence was quietly redacted before the document's public release. But the full version circulates privately among researchers now, a reminder that the simplest simulation of all, a smooth, radiation-reactive mirror following the laws of light, is the one that explains every anomaly perfectly. Still, even if the data suggests an artificial structure, there's a difference between mechanical and intentional, between a fragment and a functioning device, between debris and design. And so the next question emerged, a question that began to cross from physics into philosophy. If it isn't natural, what does that mean for how we define natural? As more scientists dared to ask that, the debate turned public, and a single phrase started appearing in journals and news segments alike, a phrase meant to sound neutral, but carrying all the unease of its implications. The phrase was the artificial debate. By the evening of November 6th, the term had gone viral in scientific circles, whispered in observatories, debated in faculty lounges, dissected in online astrophysics forums. The artificial debate. What began as quiet speculation inside private email threads now stood in open daylight. Was 3I Atlas natural, or was it something else entirely? The controversy split the astronomical community with almost surgical precision. On one side were the material realists, those who believe that however strange the data may appear, there must exist an undiscovered natural explanation. They invoked unknown carbon phases, magnetic dust aggregates, or ultra-reflective meteoritic foils. On the other side were the empiricists, those who looked at the match between prediction and observation and simply said, if it acts engineered, if it moves engineered, perhaps it is engineered. At first, Both sides tried to keep the discussion civil, but as soon as Loeb's October 31st prediction memo leaked to journalists, restraint collapsed. Headlines erupted across science media. Harvard team may have foreseen the sun's interstellar anomaly. Three-Eye Atlas, natural mirror or machine. To most scientists, the term machine felt poisonous. It carried baggage, the kind of language that drags serious inquiry into conspiracy and myth. But the facts refused to bend. Every conventional model failed. Every known mechanism fell short. And the deeper analysts looked, the more deliberate the behaviour appeared. Within 48 hours, the debate shifted from technical to existential. ESA held an emergency press briefing, insisting that no evidence supports claims of artificial origin. NASA echoed the statement word for word. Yet within both organisations, internal memos revealed quiet panic. Engineers who had run simulations saw the same thing their public relations departments denied, that the simplest way to reproduce Three-Eye Atlas's behaviour was to treat it as a functioning structure. At the European Space Operations Centre, a young analyst reportedly whispered during a late-night call, "If this were a human probe, we'd call it responsive diagnostics." That remark leaked, and suddenly the world began listening. Scientists accustomed to thinking in centuries of quiet stability found themselves forced into a narrative that sounded uncomfortably like science fiction. And yet nothing in the data had changed, only the interpretation. Public discussion fractured along predictable lines. Sober institutions like Nature, Science, and the American Astronomical Society published cautious summaries under headlines such as "Unclassified Solar Interaction Event Challenges Cometary Physics." Meanwhile, independent researchers filled the gaps with more daring interpretations. Some called Three-Eye Atlas an interstellar probe remnant, others a piece of technological driftwood, a fragment left wandering long after its creators vanished. In forums, scientists debated not just the data, but the philosophy of evidence itself. What does it mean to call something artificial when you have no proof of intention, only implication? Can design be inferred from behaviour alone? The line between engineering and emergent physics blurred. A few researchers argued for a third category, something neither natural nor constructed but self-organising. They pointed to plasmoid structures and quasi-crystalline matter, phenomena that form order from chaos without intelligence. Perhaps Three-Eye Atlas was such a system, an object shaped by cosmic forces that, by coincidence, mimics purpose. That idea offered temporary comfort, but only until data analysts noticed a new, quieter pattern, a subtle periodicity in the object's luminosity. Every 19 hours, a pulse, faint, regular, rhythmic, slightly altered its brightness. It was too slow to be rotation, too consistent to be noise. That pulse reignited the debate overnight. Some said it was thermal, the object's surface radiating stored energy at intervals. Others suspected something more, a modulation of orientation, a correction in trajectory, a system stabilizing itself, perhaps still functioning after millions of years. The pattern repeated 4 times before fading as the object receded from the sun's glare. By November 7th, the artificial debate had reached beyond science. Governments were briefed. The Pentagon's All-Domain Anomaly Resolution Office, which normally handles near-Earth aerial events, quietly requested access to ESA's data. NASA declined, citing jurisdictional limits. That refusal only fueled speculation. The philosophical implications were harder to contain. If Three-Eye Atlas were artificial, even partially, it would mark the first tangible evidence of technology beyond Earth. Not a message, not a signal, but a thing. Material proof that intelligence once existed elsewhere. The enormity of that possibility sent ripples through every field of thought, from cosmology to theology. But the counter-argument remained strong. Extraordinary claims require extraordinary evidence, and so skeptics like astrophysicist Paul Byrne and planetary scientist Michelle Bannister pushed back fiercely. They warned that humanity's first encounter with an interstellar anomaly shouldn't become an echo chamber for belief. "We've been fooled by the unknown before," Byrne said. "We mistake what we don't yet understand for intention." Still, behind closed doors, data analysts spoke differently. One ESA engineer described the telemetry as too neat to be noise. A NASA trajectory specialist said the probability of such synchronization between brightness, acceleration and magnetic response was astronomically low. The debate soon divided along generational lines. Younger scientists raised in an era of exoplanets and cosmic abundance were more open to the idea of extraterrestrial relics. Veterans, shaped by decades of caution, held the line of skepticism. One senior researcher put it simply, nature hasn't run out of surprises yet. We have. As arguments raged, a quieter question began to emerge. Not about what 3I Atlas was, but about what it might still be doing. If the object's behaviour near the Sun resembled an activation, a brief flare of energy, a pulse, a course correction, then perhaps the story wasn't over. Perhaps what we witnessed wasn't decay, but awakening. Loeb himself refused to speculate publicly, but in a private letter shared among his colleagues, he wrote one line that encapsulated the unease permeating the community. We may not be watching the past of a civilization, but its autopilot. By November 7th, the artificial debate had reached a stalemate. Every theory now existed in tension, natural but unknown, artificial but unproven, alive but silent. And while humanity argued 3I Atlas kept moving, outward, steady, fading into the black beyond Mars. But even as its light dimmed, the instrument still picked up faint irregularities, small pulses of reflected sunlight that defied prediction. The object was leaving us, but it wasn't done. Its trajectory, now bent by some invisible force, was shifting again, this time away from the plane of the ecliptic, as if deliberately avoiding the clutter of planets. And in that silence, one final question took shape, the one no one wanted to ask, but everyone felt pressing against the edges of reason. If 3I Atlas truly reacted near the Sun, then what exactly was it reacting to? The next observations, as it slipped past the orbit of Mars and toward the outer system, would reveal whether the anomaly ended with perihelion, or whether it had only just begun. Because even at the edge of its fading trail, instruments began detecting one last enigma, a lingering signature in its wake that no natural body should leave behind. That anomaly became known, quietly and almost reverently, as the deep space aftermath. By November 7th, the glare of the Sun had finally released 3I Atlas from its blinding grip. The object, now several million kilometers beyond the inner solar curtain, re-emerged into view. Faint, calm, and yet unmistakably altered. What the telescopes began to see in those first quiet hours after perihelion marked the beginning of a new mystery. The light was different, not brighter, not dimmer, just steadier. Before perihelion, 3I Atlas's light curve had fluctuated unpredictably, flickering with the uneven rhythm of solar interference. Afterward, it became unnaturally smooth. The object's brightness no longer followed the expected decay pattern, the slow fading of a comet leaving sunlight behind. Instead, it plateaued, holding constant magnitude as if maintaining a deliberate equilibrium. To an untrained observer, this would seem unremarkable, but to photometric analysts, it was alarming. Every natural body dims as it recedes from the Sun, following the inverse square law of reflected light. 3I Atlas did not. Its luminosity was regulated, as though something on or within it was compensating for distance, adjusting its reflectivity to remain visible. That pattern, the flat light curve, persisted for 5 consecutive nights. By the 6th, another anomaly emerged. Radio observatories monitoring the region noticed a faint broadband signal. A hiss, not a pulse, spanning frequencies between 4 and 12 megahertz. It wasn't strong enough to classify as transmission, nor structured enough to encode information. But it was persistent. The signal faded in sync with the object's position, vanishing when 3I Atlas slipped beyond the line of sight. The data arrived almost simultaneously from 3 separate instruments: the Allen Telescope Array in California, the Nancy Observatory in France, and Japan's Yasuda Deep Space Center. All recorded the same narrow arc of noise. The shape was identical in each. At first, everyone assumed solar interference, but solar weather was calm. No flares, no bursts, no coronal ejections. The Sun was quiet. The only thing moving through that region of space was 3I Atlas. ESA's analysis team labelled it plasma resonance interference. That was the official line, but privately, engineers found the explanation unsatisfactory. The emission frequency wasn't random. It followed a slow oscillation, repeating roughly every 19 hours, the same rhythm that had appeared in the object's post-perihelion brightness pulses. A coincidence, perhaps, but if it wasn't, then 3i Atlas was producing a signal that resonated with its own light. More data followed, and with it, a pattern. As the object moved outward, a faint invisible halo began to trail behind it, detectable only in polarized light. The shape wasn't diffuse like dust. It was filamentary, long, thin, braided structures stretching for thousands of kilometers. Their polarization angle rotated slowly over time, as though twisted by a residual magnetic field. This afterglow wasn't a tail in the conventional sense. It didn't scatter sunlight, it bent it. The light from background stars passing through the region showed minute but measurable distortions, gravitational lensing too weak for the object's mass. The only possible cause was refraction by a structured plasma field. In other words, 3i Atlas was leaving behind a corridor, a tunnel of disturbed space, still active long after the object itself had passed. That corridor, now known as the afterwake, became one of the most puzzling features of the event. It extended tens of thousands of kilometers, fading only gradually, like an ionized fingerprint burned into the solar wind. The Parker Solar Probe recorded residual magnetic tension along its path for nearly 12 hours, as if the object's electromagnetic field had persisted long after it was gone. When researchers mapped the direction of the wake, another oddity surfaced. It didn't align perfectly with the object's trajectory. It curved, gently, consistently, toward the ecliptic north, diverging by nearly 3 degrees. That deflection made no physical sense. The solar wind should have carried the wake in a straight line, trailing the object. Instead, it arced upward, as though pulled by an unseen vector. NASA's heliophysics division attempted to simulate the effect. The only model that matched reality required one improbable parameter. The wake retained residual current, as if magnetized particles within it were moving under guidance, not dispersion. Guidance implies a continuing source, but 3i Atlas was already hundreds of thousands of kilometers away. Nothing about it should still be interacting with the space it left behind, unless, as one theorist dared to suggest, the wake itself was part of the object, an extension, not a byproduct, a field, not a trail. That possibility shook even the skeptics. If the wake was cohesive, it might mean 3i Atlas carries or generates a localized plasma sheath, something that remained active even as it drifted outward. Such sheaths exist around spacecraft using magnetoplasma propulsion. They're called mini-magnetospheres. The resemblance is uncanny. By the second week of November, telescopes confirmed that 3 Atlas's brightness hadn't faded with distance as expected. Its apparent magnitude remained constant at roughly 17.6, the same as it was just after perihelion. The implication was extraordinary. The object was either expanding its reflective surface or emitting faint luminescence of its own. Some scientists proposed a last-ditch natural explanation. Luminescent gas ionized by solar UV trapped in a localized pocket of magnetic flux. But that theory collapses under one simple fact. The emission persisted for more than a week, long after solar energy could sustain it. Others pointed out that the halo's orientation continued to shift, aligning more and more toward interstellar space. Not random drift, but vector realignment. It was as if 3i Atlas had reset. The idea spread quietly. Perihelion wasn't destruction, it was reactivation. A dormant structure travelling for millennia through deep space, briefly exposed to the sun, might have absorbed enough radiation to reboot, to reawaken whatever systems or materials lay dormant inside. That speculation remains unproven, but it fits the timeline too perfectly to ignore. Before perihelion, inert, during, chaotic, after, ordered. In astrophysics, that sequence describes one thing only: ignition. And if 3i Atlas ignited, then its silence now isn't the end. It's the beginning of an outbound phase we can't yet model. As of November 7th, it continues to accelerate slightly faster than solar gravity allows. The direction of that acceleration is no longer radial from the sun but oblique, angled toward the interstellar void above the ecliptic plane. No comet has ever done this. The numbers are small, fractions of a meter per second, but consistent. It's steering itself away from us, or something is guiding it. The wake fades. The radio hiss weakens. The halo dimly persists. And for the first time, astronomers find themselves describing an object that doesn't seem to belong to any known category. Not a comet, not debris, not even a probe, just a presence, silent, deliberate, vanishing into the black beyond Mars, leaving behind a thin thread of radiation like a ghostly exhale from something older than our species. Soon, it will pass beyond the range of our telescopes entirely. Its signal will flatten into noise, its light into darkness. But before it disappears into that long silence, there remains one final task for the observers of 3I Atlas: to decide what they have actually witnessed. Because if this was a machine, it's gone. If it was natural, it was never truly understood. And if it was neither, if it was something in between, then what we've just seen isn't the end of a mystery. It's the beginning of a new category of existence. For now, we only have the data, the faint pulse, the residue, the unbroken trajectory slipping into infinity. And somewhere, between the physics we know and the silence we cannot measure, 3I Atlas continues, a fragment of purpose moving through a universe that has forgotten what built it. Its light grows fainter each night, but its shadow, the questions it left behind, has only just begun to form. Tonight, as the last confirmed observations of 3I Atlas arrive, the instruments fall silent one by one. No new flares, no deviations, no further signs of activity, just the slow, constant fade of an object that refuses to behave like anything we understand. The data tells us it is still accelerating, so slightly that gravity alone can't account for it, yet steadily enough that each night its projected position drifts further from the models. It is leaving not only the sun's influence, but the reach of certainty itself. Scientists now call this stage the departure epoch, the point at which an interstellar object leaves behind more questions than evidence. For Oumuamua it came quickly. For 3I Atlas, it lingers, like an unfinished sentence. The wake behind it remains faintly ionized, a ghost corridor through which the solar wind moves differently. No telescope can explain why it still exists, or why its orientation continues to tilt northward, away from the galactic plane, as though aligning with something unseen. And so the community has settled, reluctantly, on new language, words that admit doubt while disguising awe. Not artifact, not vessel, just anomalous interstellar reflector, a phrase that says nothing and hides everything. The real argument now isn't about what 3I Atlas is, but what it means. For decades we assumed that discovery would come with clarity, that proof of the extraordinary would announce itself unmistakably. Instead, we're left with ambiguity, a line of data, a handful of impossible correlations, and the quiet knowledge that somewhere out there, an object behaved as if it remembered how to move. No message was heard, no technology was recovered, only patterns, too precise for comfort, too incomplete for certainty. Yet something changed. The maps of the solar system now include a dotted line stretching beyond Mars, marked not as a comet, not as debris, but as 3I Atlas, unclassified. A new category, a new silence. If it was natural, it has redefined what nature can build. If it was artificial, it has redefined what intelligence can leave behind. And if it was something in between, matter that learned somehow to respond to light, then perhaps our universe is less inert than we ever imagined. For now, all we can do is watch the numbers fade on the tracking screens. The coordinates grow colder, the signal weaker. In a few days it will be gone, out of range, out of data, out of words. And yet, even as the last reflection vanishes, a question remains suspended in that darkness, waiting for whoever might one day follow its path. Was 3I Atlas merely passing through our star's light, or did it come here to see how we would react to it?